Okay, let's unpack this. We are doing a technical and atonomic deep dive into a really revolutionary platform in the energy sector, the Kepler Texatron. For decades, fusion has been defined by these two main schools of thought, these massive government-funded machines. But this is, well, it's something fundamentally different. It's a novel design, and it's paired with a very immediate, very aggressive corporate strategy aimed at commercial deployment.
That really is the crucial distinction here. If you look at the history of controlled thermonuclear fusion, the whole field has been dominated by magnetic confinement fusion. So we're talking about large-scale projects, the steady-state tokamaks and stellarators. And then on the other side, you have inertial confinement fusion using these huge laser arrays. The Texatron platform, it doesn't really fit neatly into either box. It introduces a kind of hybridized, fast-pulsed torsatron configuration.
And the mission for you, the listener, is critical. We need to understand the physics of this departure, how this system actually works, its radical aneutronic fuel strategy. And then we need to trace the corporate maneuvers that are trying to establish this new public entity, American Fusion Inc., as an immediate leader in the commercial power as a service, or PES market.
Right.
This transition means we're basically watching a physics experiment morph into an infrastructure investment, and it's happening in real time.
Exactly. This deep dive requires us to connect highly complex plasma physics directly to market strategy, because the technical choices that they've made, things like the compact size and the fuel, are what allow their aggressive economic model to even exist.
So let's start with the architecture itself. This is classified as a fast-pulse torsatron. Now, most of our listeners will be familiar with the tokamak concept, but a torsatron, that's less common. How do we define it, and where does that name, Texatron, even come from?
A torsatron is a variant of the stellarator, which is a toroidal or, a donut-shaped magnetic confinement device. The core function is the same. It's to twist the magnetic field lines so the superheated plasma stays contained and doesn't hit the reactor walls. The name Texatron is a portmanteau. It reflects the platform's development origins in Midland, Texas, combined with its torsatron configuration.
Okay, so if the stellarator and the torsatron both serve that same purpose of confinement, what's the specific engineering advantage that the Texatron's geometry provides over a traditional stellarator?
It really comes down to manufacturability and stress management. Stellarators are, frankly, notorious for requiring these incredibly complex, non-planar magnetic coils. The coils are twisted in multiple directions, and that leads to enormous, highly varied electromagnetic stresses on the structure. The Texatron simplifies this dramatically. It uses twisted, donut-shaped coils where all the high-current electric currents run in the same direction.
It's the same direction.
Exactly. This unidirectional current flow minimizes those localized asymmetric electromagnetic stresses on all the components.
And the benefit of minimizing that stress is?
It enables the core feature of this platform, the ability to build a far more compact, more modular, and potentially even portable reactor unit. If your structure isn't fighting itself electromagnetically, you can scale down the physical size without compromising the integrity of the containment. This is foundational to their claim of a reactor that can be, truck portable.
But unlike those traditional, very large torsatrons, which are designed for continuous, steady-state operation, this device is explicitly pulsed. How does that change the fundamental process?
The pulsed operation is the key departure here. It really moves the system into the realm of magneto-inertial fusion, rather than pure magnetic confinement. And this mode, it dictates the use of a very specific mechanism for establishing the precise magnetic geometry very, very quickly. This is achieved via something called a rifled toroidal pinch, or RTP conductor.
That sounds highly technical. If the magnetic configuration is what's holding the plasma in place, how does this rifling conductor manage such a complex task in just a split second?
Well, think of it like a gun barrel. When you fire a bullet, the rifling spins it, and that stabilizes its trajectory. The RTP conductor acts in a similar way, but for the plasma equilibrium. The final, stable helical magnetic configuration that's needed to hold the plasma is defined by geometric conservation principles, the flux invariants. And these are imprinted onto the initial plasma by the shape of the RTP conductor itself.
So the rifling, the shape of the conductor, mechanically and electromagnetically determines the final geometry.
It dictates the precise geometry the plasma will adopt as the pulse rapidly compresses it. It ensures stability right before the fusion reaction begins.
And that rapid pulse, it's not just for geometry, it's also how they heat the plasma to fusion temperatures. How is that temperature profile achieved so quickly?
The heating process is twofold, and it's synchronized with the pulse. First, as the magnetic field rapidly increases, it induces a transient plasma current inside the fuel. This current causes resistive heating, often called ohmic heating.
Like in a toaster element.
Exactly the same principle.
But resistive heating alone isn't nearly enough to reach the millions of degrees you need for fusion.
Correct. The second method is the dominant one here, shock heating. The extremely rapid increase in the external magnetic pressure launches a cylindrical shock wave that converges inward, toward the magnetic axis of the reactor. This shock wave acts like a hammer, compressing and adiabatically heating the plasma with extreme efficiency.
And this isn't a purely theoretical concept.
Not at all. This method, using converging shock waves to reach fusion temperatures, has been validated in prior high-energy density physics experiments. We're talking about work done at places like Los Alamos National Laboratory. It's a mechanism that's uniquely suited to this kind of rapid, pulsed energy delivery.
So they're leveraging speed and compression efficiency to compensate for the device's smaller scale. Okay, let's shift from the mechanics to the plasma properties. The Texatron is a high beta device. We should be really clear about what plasma beta signifies.
Plasma beta, denoted by the Greek letter bak, it's a fundamental dimensionless metric in fusion physics. Simply put, it measures the efficiency of the magnetic confinement. It's the ratio of the thermal pressure generated by the plasma, so how hot and dense it is, to the pressure exerted by the magnetic field that's required to hold it.
Right, so it's about getting the most containment from the smallest or cheapest magnetic field. Why is operating at high beta so essential for this specific design and, I think crucially, for its economic viability?
Conventional large-scale tokamaks typically operate at very low beta. This means they need huge, extremely powerful, and very expensive superconducting magnets to hold a relatively less energetic plasma. The Texatron, on the other hand, leverages principles from physics like the Wells-Taylor invariance, and it operates at high beta. This high efficiency means they can achieve the necessary fusion conditions, the pressure and temperature, with significantly lower magnetic field requirements.
And the direct economic consequence of that is?
A radical reduction in capital costs. The superconducting magnet system is one of the most expensive parts of any fusion reactor. By needing less powerful magnets, and therefore smaller and cheaper magnets, they just lower the entire barrier to entry for commercialization. High beta equals lower hardware cost.
That lower cost structure ties directly into their fuel choice. This is the other major differentiator for the platform, the deuterium-helium-3 cycle. This is the definition of aneutronic fusion.
It really is the holy grail for commercial deployment. The primary reaction is deuterium plus helium-3 fusing to produce a standard helium-4 nucleus in a high-energy proton. This strategic choice to pursue DHE has profound implications for the design, the safety, and the ultimate cost structure of the reactor.
Let's contrast that for the listener with the much more common deuterium-tritium, or DT, fuel cycle. DT is what most of the big global fusion efforts are focused on. Why is D so much better from an engineering standpoint?
The contrast is fundamental. The standard DT reaction releases 80% of its energy as high-energy neutrons. These neutrons they're terrible for reactor health. They cause severe neutron embrittlement, which degrades the structural integrity of the reactor walls over time. And they create long-lived radioactive waste, forcing the facility to incorporate heavy biological shielding. We're talking meters of concrete, and requiring specialized, prohibitively expensive materials.
And DHE avoids all of that.
Virtually all of it. Since the DHE reaction is primarily aneutronic, it produces only charged particles, the helium nucleus and the proton, instead of those highly penetrating neutrons. This eliminates the need for massive shielding. It drastically reduces the problem of long-lived radioactive waste. This is the second key variable that allows them to use standard and industrial-grade materials and achieve that compact modular form factor we talked about.
Which leads to the final piece of the technical puzzle, the ability to achieve direct electricity generation. If the process only produces charged particles, how does the Texatron turn that energy directly into usable power?
This is the ultimate efficiency game. Because the reaction products are 100% charged particles, they are inherently tied to the magnetic field lines. When the fusion-heated plasma expands against the confining magnetic field, a direct result of that high pressure, it acts like a piston pushing against those fields.
Which then induces a current.
Precisely. This expansion induces a current in the external coils via Faraday's law of induction. This direct conversion architecture lets them bypass the entire complexity, the inefficiency, and the massive size associated with conventional thermal systems.
So no steam cycles, no boilers, no turbines.
None of it. The things that characterize every traditional power plant are just gone.
And that's not just about maintenance costs, that's about energy loss. We're talking about theoretically massive efficiency gains, right?
Yeah. Immense. Thermal power plants are governed by the laws of thermodynamics, specifically the Carnot limit, which constrains how efficiently you can convert heat into mechanical work. By converting the kinetic energy of charged particles directly into electricity, the Texatron can theoretically operate with an efficiency far beyond what any thermal system could ever achieve. If they can scale it, it's a game changer.
Okay, so we have the three technical pillars for low capital cost: compact geometry, high beta operation, and Aneutronic fuel. Now let's pivot to how they plan to take this to market. The platform is undergoing a major corporate transition.
It is. It's an aggressive maneuver, clearly designed to accelerate funding. Kepler Fusion Technologies, which was a subsidiary of Kepler Aerospace, is merging with Renewal Fuels, Inc. That's a company that currently trades over-the-counter, ticker RNWF. The resulting public entity will be renamed American Fusion, Inc.
And I see they're also planning to re-domicile to Texas and seek a listing on the new Texas Stock Exchange, the TXSE. What's the significance of that?
Well, that move is partly symbolic, aligning with the Texas energy and tech sector. But more importantly, the merger and uplisting will require the company to complete a PCAOB audit. That's the Public Company Accounting Oversight Board. And that audit is the gold standard for financial transparency. It's absolutely necessary if they want to move off the OTC market and list on a major exchange, validating their financials for serious institutional investors.
And the commercial value of this new entity, it's anchored in its intellectual property strategy. How comprehensive is their IP defense?
Their approach is to build an extremely robust legal defense. We're talking about a pipeline of 238 patents and trademarks. This is what's commonly called a patent thicket. It's designed to protect every conceivable aspect of the design and operation, making it nearly impossible for competitors to engineer around their core breakthroughs.
You cited one specific patent as being very important. Patent hashtag 12,063,874 issued in 2025. Why is that one so critical?
That patent covers extremely low resistance materials, which are essential for their specific superconducting magnets. Remember, high beta reduces the required strength of the magnets, but they still need to be highly efficient. This patent validates that the company possesses unique, non-obvious technology in superconductivity, a field that is often the bottleneck for compact fusion. It's tangible evidence of advanced proprietary engineering.
Now, for the revenue model, they're pursuing a power as a service or PaaS model instead of just selling reactors. Explain how that works.
American Fusion intends to operate as an infrastructure company, so they will retain ownership of the fusion units, the Texatrons, and operate them. They'll then sell the electricity directly to customers under long-term power purchase agreements, or PPAs. This gives them a predictable, utility-style revenue model, which is highly attractive to infrastructure funds.
And what are their economic targets? They have to be competitive to get anyone to switch from established baseload power.
Their publicly stated target is approximately 6.25 cents per kilowatt hour. That price point is strategically chosen to be competitive with, or even slightly below, the cost of many conventional baseload power sources, like natural gas peaker plants. And that low price is only viable because of the technical savings we've been discussing, the low capital cost and low operational costs.
So who are the ideal customers for this new power source?
They're targeting three distinct, very energy-intensive markets. First, AI data centers. They need continuous high-density power that absolutely cannot be interrupted. Second, defense installations, which are seeking true energy independence with truck-portable units for remote or critical sites. And third, various heavy industry facilities that require huge, localized electrical input.
We have to address the elephant in the room here, the extremely compressed and frankly aggressive timeline. What are the current goals for prototype version 9 and what are the major corporate milestones?
The technical team is currently focused on testing prototype version 9 down in Midland, Texas. The primary goal is validating the stability of that RTP induction mechanism and confirming the efficiency of the shock heating.
Making sure the physics holds up at scale.
Exactly. Corporately, the schedule is highly ambitious. The PCAOB audit is slated for completion in February 2026, and the critical goal is the deployment of a 100-megawatt operational pilot unit in North Texas by late 2026. A 5-year timeline from concept to commercial deployment is it's unprecedented in fusion.
And given that timeline and the claims, a 30-megawatt reactor that fits in a pickup truck's skepticism is guaranteed. Before we get to the critics, let's establish the scientific credibility of the leadership here.
The project is helmed by its chief science officer, Dr. John Brandenburg. He is a respected plasma physicist. He has a technical background from places like Lawrence Livermore National Laboratory, and he led NASA's CMTX project. And crucially, the Texatron concept was presented at the 2023 American Physical Society Division of Plasma Physics meeting. That means the underlying science is considered a legitimate, peer-reviewed topic in the community.
However, the scam narrative does surface. Critics point to the extremely compact size, and often to Dr. Brandenburg's other non-fusion theories, specifically his controversial ideas about a lost civilization on Mars, to try to dismiss the technology. How do we, as impartial observers, navigate that kind of charged environment?
Well, we have to separate the individual's personal theories from the documented proprietary technology being developed. The technical counter-argument is that the Texatron has submitted its results to a legitimate scientific forum, the APS. And furthermore, that crucial IP, like the patent for their superconducting materials, is tangible evidence. It shows they've passed the non-obviousness test required by patent law. This provides an objective measure of technical uniqueness that really transcends individual personalities or any controversial side projects.
So the market view seems to be that this is extraordinarily high risk, but it's grounded in proprietary tech.
That's the consensus captured by market analysts. Harbinger Research, for example, categorized the stock as a strong speculative buy. Their assessment was explicit. They said the project is high risk because the physics is difficult, but they affirmed it is not a scam. They see it as a proprietary and extremely difficult technical feat that, if it succeeds, offers returns that could reshape the entire energy investment landscape. It's what they call an asymmetric potential outcome.
So to synthesize the potential here, the Kepler Texatron is this ambitious integration of technical breakthroughs, the mechanical elegance of the torsatron, post-power, Aneutronic fuel all engineered to solve the economic and deployment issues that have plagued large fusion projects.
And if they meet their aggressive 2026 deployment milestones, the implications are just enormous. A modular, clean, highly efficient power source that can be decentralized would fundamentally re-engineer the energy grid. It would shift the balance of power generation away from large centralized plants toward localized infrastructure.
And their vision goes far beyond just terrestrial power, tying back to the company's roots in Kepler Aerospace, this idea of energy-space synergism.
Precisely. Because the deuterium helium-3 fuel is abundant off-world, particularly on the moon and the gas giants, the Texatron design is positioned as a potential power source for deep space missions and future lunar bases. It integrates power generation with potential propulsion systems, like their work on the Kepler drive and MET thrusters. It bridges energy infrastructure with deep space ambition.
This deep dive really illustrates the intersection of advanced plasma physics and ambitious infrastructure-grade corporate strategy. They seem to have solved many of the physics and crest problems on paper. Given American Fusion Inc.'s aggressive 2026 target for that 100-megawatt pilot unit, the crucial question for the industry now shifts entirely. It's no longer, is fusion possible? But rather, can the immense complexity of magneto-inertial plasma compression, this very specific technological approach, be successfully industrialized, manufactured repeatably, and scaled on a compressed timeline of just 5 years? That industrial challenge, that remains the ultimate gatekeeper for this next generation of power.